Back to another video, guys. We are gonna go through 2D shapes, rectangles in this case, but the ideas actually can be extended to any types of 2D shapes. Okay, in this case, we're gonna go through scaling. Okay, you remember that if two triangles, let's say triangle 1 and triangle 2, if they're nested, so that they actually have all angles the same and proportional sides, like in this case, so you can state that two triangles are similar. In this case, you definitely have a scaling or enlargement with scale factor. Okay, so that's an idea. If you have the scaling ratio, let's say any size, the small x from that point to that point, to the whole, let's say, big length of y, okay, and that triangle from that point to that point. So actually you have the ratio of linear sizes, and let's say it's going to be, let's say, 1 to 2. So you have definitely scaling with a factor of 2 if you enlarge the small triangle with a side of x. How the areas are interrelated? The answer, and pretty obvious, so if you like you can prove, maybe I'll give your proofs a bit later. So the areas are interrelated as the square of that ratio, so that's why the areas of triangle, of the small triangle, the size x, linear size x, to the area of the larger triangle with the side y is going to be related as x squared to y squared. So that means is 1 to 4. So in other words, the scaling factor, in this case, k, 1 over 2, and you raise the scale factors to the power 2 in order to get the ratio for the areas. What about volumes? You can even more extend that to the volumes ratio. So Vx to Vy, in this case, V stands for the volumes, is going to be related as k cubed, okay? But right now we are going to limit ourselves to the areas. So that's why let's consider this problem that I found pretty nice in order to demonstrate that, okay? Pause the video, try to do by your own, and let's get started. Okay, you're given two rectangles which are definitely similar. They have BF to FD as 2 to 4, okay? And you need to find what's the ratio of the area of quadrilateral BFCM. So I just shade this quadrilateral. In this case, it's definitely trapezium because they're rectangles and those sides are parallel. So side BC is parallel to FM, okay? So that's why you're looking for the area of quadrilateral shaded here to the area of triangle FMD. So FMD is right there, so I'll also shade this. So in this case, that's FMD. Okay, so let's try to do and establish that area. Let's say quadrilateral I set up like this, okay? This is BCMF, and the area of triangle I just set up like this. This is triangle FMD. That's what we need to find, okay? So, but instead of area of this trapezium, I just simply use their idea of integral parts. So BDC is the larger triangle that contains your quadrilateral, and if we subtract from the area of the triangle BDC, if we subtract the area of the smallest triangle FMD, which I set up like triangle, so, and divide by parts, we'll get actually the ratio of area of triangle BDC, okay, the big one, to the smaller triangle and minus 1, okay? So that's why right now we are supposed to find the ratio area of the largest triangle to the area of the smallest. As you can see, they're definitely similar to each other. So indeed, if you start exploring the angles, so the second line and two parallel lines, right, as we notice here, and the right angle right there, again, for the same reason, two parallel lines, and the second line CM. So we have all three angles, and this angle at the vertex D obviously the same for both triangles. So they are similar. Triangles are similar. In this case, we can figure out that areas, so this ratio is simply as the k squared, right? Where k is a scale factor. So that's why right now we're gonna go and try to find that. Of course, we're gonna use this ratio for scaling, and let's try to figure out. Right now you're given just only BF to FD. So BF is a small one, but we would like to have BD, right, to FD. So right now we're looking for the ratio BD to FD. That was k factor represent, okay? So, but we're given BF to FD. So that's why we need to come to this ratio from the ratio that we are given. But first, I would like to simplify that quick. So 2 to 4 is 1, 2, 2 in the simplest form. So BF, if you want to find the ratio BD to FD, we understand that actually, in our case, we have 3 parts in total. So that's why we can consider as, so FD, we can express through BD right now, okay? Which way we have 3 parts? Yes, so that's why FD is going to be 2 over 3 of BD, okay? From the ratio that we're given. In other words, we have FD, just let me explain quick how I get it. So FD is actually 2 over 3, yes, 2 parts over 3 parts in total out of the whole BD length, okay? So 2 out of 3 of BD. So that's how I get this. And right now, if we plug that into the ratio BD to FD, expressed in this way, we can get that BD to FD represent the ratio 3 to 2. Okay, so we just simply plug FD 2 over 3 BD, we cancel that, and in reverse the fraction 2 over 3. Okay, so we've got this ratio, and that's why this is the scale factor k. So that's why k squared is going to be 9 to 4. So that's why the answer to the question A was the ratio, simply 9 over 4 minus 1. So the final answer to the ratio quadrilateral area to the area of this triangle FMD is going to be 9 over 4 minus 1. Okay, and if we simplify that, we finally get the following. Just squeeze a little bit. So finally we get that the area, final area of this quadrilateral to the area of the triangle. So 4 and 5 over 4 as the result. So this is the answer to the question A. So what about question B? Let's fix this answer. Move to the next page, so to the next line. If AD is 1.5 AB, so we fix that. AD is 1.5 of AB. And AB is 12. So that's why we need to fix that side. So that side is actually 12 right now. So this 12, and because AD is the same as BC, so I would use, no matter which side I'm going to use, let's say BC, that's going to be the same as AD because it's rectangle. It's 3 over 2 of AB. So 3 over 2 out of 12, so that means it's going to be 18 centimeters and 12 centimeters. Now we know the parameters. What's the area of quadrilateral BFCM? Okay, so let's calculate the area of the quadrilateral. So area of the quadrilateral is simply just go back. So every quadrilateral, if we express through that ratio, we multiply both sides by the area of triangle. So that's gonna be 5/4 of the area of triangle. And triangle is FMD. So that's why we fix that and we write in as 5/4 of the area of triangle FMD. So that's why right now we can find the area of this triangle. But again, we're coming back to where we would like to understand that area of this small triangle is, let me see, it's k squared. So that's why it's 4/9, right? It's 4/9 because the linear size FD is 2/3, so k factor is 3/2, right? 3/2, that's scale factor. So that's why it's going to be 4/9. So we're diminishing that. So it's going to be 5/4. Area of triangle of smaller triangle is simply 1/k squared of the area of the largest triangle, which is DBC. Okay, so that's why we can write that it's 5/4 times the area of the triangle DBC and 1/k squared. So 1/k, just going back, 1/k is going to be 3/2. So that's why it's 2/3. It's 2/3. When we square this up, we'll get 4/9. So that's why we just apply this factor 4/9 and we still multiply by the area of the triangle DBC. But hold on, so area of the triangle DBC is what? Let's have a look there. So area of triangle DBC is the half of the area of the whole rectangle. So area of rectangle ABCD is 12/18. Okay, let's multiply 12/18. It's going to be 216. And area of the triangle is half of that. Yes, it's 1/2 of 216. So that's why it's 108. So area of triangle DBC is simply 108 centimeters squared. That's why we can plug into our formula and we'll get 108 there. Okay, so that's the final area for the quadrilateral. Now it's time to multiply. So 4 is cancelled there. So 5 times 108 and over 9. If you calculate that, so 5 times 108 and over 9, we'll get 60. It's going to be 60 centimeters squared. That stays for the area of the quadrilateral. Hope you like that. That was pretty, I think, challenging in order to get those details, but I think it's good demonstration for the scaling process and your actually math skills that you can apply to similar problems. Okay, so I hope you like that. If you're new here, don't forget to subscribe to my channel. You'll see actually explore lots of stuff that you might need or you might have help with. So, and don't forget to visit A-level Zillion's class. All right, that was Daniel Dallas. See you next time. Peace.